Welcome all of you. Sorry for delay. So we'll gonna start the today's session. So first I will introduce myself. So I'm Vijay Ran and I'm a Prime Minister Specifically in the IIT Delhi. And today we are here for the some to solve some of the problems on this course molecular rearrangement and reactive intermediates in the organic synthesis. So today, before going to the problems. So I would like to take if you have any doubts regarding this week 5 or the week 6 content which are covered by the professor on the NPTEL platform. So if you have any doubt, please let me know. We'll discuss that one first before going to move toward the actual some problem that I have taken from the old assignment. So we'll discuss that problem now. All right, if you don't have any problem, I will move to the some of the question and which is basically based on the some of the intermediates. Like today, the topic is radical benzyme intermediate and also the carbocation, all the intermediate. So it will be combined of the all the intermediate that we have seen in the from the week 1 to the week 6 of this right. So here is the first question. So which mention predict the major product in the following reaction. So you need to uh, I'll just yeah. So this is the reaction condition which you have given, and so among this, what will be the major product? So you have given one starting material and the product. So is there anyone able to solve this question? Anyway, I'm going to solve this one. But if you have any, if anyone have any answer for this one among this one, so please let me know. So we'll discuss that one. So this is the if you remember this reaction condition. So this reaction condition is the for the burst reduction reaction, right? So first the name is the name of this reaction. So which involve the sodium in liquid ammonia and this all these in the obviously there will be a solvent THF or most of the time the solvent is THF and then catalytic amount of the ethanol after the reaction. So this is the first and the second is the ethanol. So what happens in this reaction? So this is the burst reduction reaction condition, right? And so if you look at the burst condition, so it basically if you have such aromatic system and when this aromatic system react with the sodium in liquid ammonia, it forms a electrolyte salt plus one electron, right? And this free electron basically transfer to the this electron transfer to the aromatic system and what happens, so this aromatic system goes in this manner converted to this way. So basically here there was initially hydrogen and there is now negative charge and these are the two bonds which are present earlier and this is the new incoming electron. So what happens, so this is the electron, both electron goes here and one electron which is comes from the combination of the sodium and triethylamine. So the triethylamine, not only single molecule, this triethylamine there will be n number of triethylamine, not a single. So it will be like Na plus, and there is coordination of NH3, NH3, and this sort of multiple. There will be not such direct bond, but there will be a chelation, we can say, with this. with this sodium cation, right? So this is how it goes. And now further course of reaction and the selectivity and all will go through the stability of this radical and also the stability of this negatively charged. So now, if you consider the mechanism of this Birch reduction reaction, now this ethanol, the carbonyl acid, it is a electron withdrawing group. Now, it depends upon whether the group attached on the benzene ring, whether it is electron donating or electron withdrawing. So the course of reaction goes. So here, as we have the electron withdrawing group on the benzene ring, now in this case, what happens? So once this so here, this was just because of this basic nature of the solvent. So it calls a negative. That's just you can ignore. So this entire group is basically electron withdrawing group. And now the radical, radical goes to the this position, and negative charge will be on the this position. So there will be intermediate step. So I will just draw that intermediate step. So once it forms like this way, so this is the electron withdrawing group. Now this bond, this radical goes here, the negative charge goes here, and upon further delocalization, this negatively charged on the ring will goes to the here. This bond will be here, this bond will be here, and here there is the electron withdrawing group. And this is the same. So the proton at that position that will be remain same. So that will not gonna change, right? So I'll just draw the negative charge instead of drawing the, yes, I'll draw the proton as well for understanding. So, right. So we are up to here. This is the intermediate. And if you look at the intermediate, so the negative charge is on the here. And another possibility for this stabilization of this negative charge. So there will be, so delocalization of this negatively charged. Negative charge can go to the, that position also. How this will go? So obviously it is again on the based on the delocalization. Delocalization, and again, okay, and if you just delocalize this negative charge, so from this one, so the delocalization will be here, the negative charge. Now the bond position is here, and here there is the negative group, and here that was the radical. And we can also write the same. So uh, so as we draw on here the negative charge, sorry, the radical and the negative charge, this is again one of the possible resonance structure. And in this case, what happens when this species react with the ethanol, it is a source of proton. So the negatively charged directly abstract the proton from this ethanol, and it goes to this the new proton come from the ethanol, and this will be a intermediate step. So once this proton is formed, sorry, proton is attached here. Again, another molecule of this NH3 and this Na plus and one electron plus this one electron. This transfer to the this radical, it becomes a negative charge now, because earlier there was one electron, now again one electron comes to this position. So it will be negatively charged now. And this negative charge again abstract the proton from the ethanol. It will goes here. So this is how the reaction works in case of the when the benzene ring has the electron withdrawing group. When there was a electron donating group, so that time, so if you consider here, so this will be electron donating group at that time. So I'll just the product will be in this manner. So this group will be remain and this on the same position. So electron donating group, right? And it will be like this. So there will be a proton. So this is the case with electron donating group. And in this case, it is a electron withdrawing group. So that's why. So in case of the, I will also draw for the electron withdrawing group. I will just erase all this remaining. which is not necessary. Like I'll just draw the, in case of the, when we have the electron withdrawing group, in the same case of this electron withdrawing group. So in that case, I will directly draw the product. So in the same mechanism, so there will be, the product will be like this. And here is a proton, and here there is an electron withdrawing group. So you can just keep remember. So when you have the first case, the electron withdrawing group, so that time the product will be in this manner. And when there is the second case, there is an electron donating group. So the product will be like this. And this is the starting material. So all right. So earlier case, the what will be the product in this case? You can directly answer now. So here, this is the C double bond OH, which is a electron withdrawing group. So in that case, the product will be like this. So there is a hydrogen, there is an electron withdrawing group, and here the two hydrogens, right? So you can match the answer. So all right, so this is the answer. So they are wrong answers in this case. So this is basically a Birch reduction reaction. And also this Birch reduction reaction is also, I have mentioned last time, it is also used for the formation of uh, alkene from the alkyne. So the same Birch reduction condition for conversion of, let's say here this is R1, and which has C triple one, sorry, C, and here there is again R2, and if you want to if you want from this one two, so this is the R2, this is the R1, and the incoming new protons. So if you want this product, so you can use the same reaction condition, sodium in NH3. So you can use this condition, and you get the trans alkene, and this was the alkyne. So what is the intermediate involved in this one? So when this reaction react with the one electron takes one electron, it forms the R dash, and here there will be C triple bond, sorry, double bond now, and there will be a R2, and this is the negatively charged, and this is the radical. And also if someone mention why not this one, let's say why not to you decide. Yeah. If someone mention why it is not forming a cis, this is because there will be a radical and there will be a negatively charged. Obviously, it will have the two electrons. So I'll just this is the radical, right? And this will be a two electrons. So there will be a steric repulsion in that case. Let us draw with some other color. Uh, Not steric repulsion. There will be a repulsion due to same charges. And here that's why major. So this the trans one will be the major. So now you obviously know the course of reaction, how it will further convert into the alkyne. So that I don't think I need to draw. So it will go convert into this one. So there will be two steps. The first step will be formation of. So it takes the proton from the solvent, the ethanol. It takes proton, it forms a hydrogen at this position, hydrogen, and then again another electron from the sodium and triethylamine combination, sorry, that ammonia combination. It gives the another proton, another electron, and it forms negative charge at this carbon as well. And again, it's also take the proton. So that's how the for the reaction works goes. So there will be a two intermediate step. So there will be a first step is the proton, the second step is the electron transfer, and third step will be again the proton from the ethanol. This proton abstraction and this electron transfer. So they are the between steps. So we get the trans alkene as a major product, right? The next question is the based on the TiCl3 DME. That's the titanium fluoride and zinc copper combination in the at room temperature. These are the if you look at the structure. So we have the two aldehyde in the starting and TiCl3 complex as a catalyst we have given, and what will be the major product formed in this reaction that you need to identify. So anyone have any answer for this one? I recommend to please speak because if you have any doubt, you can clarify that one right now. All right. If anyone doesn't have any answer for this one, I will solve it for you. So if you look at this reaction, this is the pinnacle reaction, and this pinnacle reaction gives the formation of cis alcohol. So keep in mind. So this is the pinnacle reaction. Whenever we have the such alcohols at the 1,5 position, so one, two, three, sorry, fourth, this aldehyde groups, it gets converted into the corresponding alcohol, and thus is cis, or we can also call it as syn geometry, syn diol. Next question is again on the similar type as we have seen earlier. Uh, we have the sodium and ethanol in the hexane solvent, and the starting material is the ester. What happens when this ester react with the sodium? So that's what you know to solve here. So basically, sodium, if you have sodium or the lithium, so they are generally source of electron. So the electron might go from the this ester to sorry might transfer to the ester. So this ester takes an electron. So I will directly go by mechanism. So in this case, you can see I just draw the this entire phenyl group as a short form pH, and we have the carbonyl group. So CH2PH. When this sodium transfer the electron to this one, so the at which center this electron transfers at this carbon center, right? So this was the center. So and this OME will be remain same. So I'll just so this was the earlier it was like O and O. This is the methyl, right? So now one electron flows from so this electron goes here, right? And the negative charge goes to oxygen. So this is the same and that I have drawn here. Negative charge goes here, right? Then in case of the solid, we have the proton. So that proton is getting abstracted. Now again, another molecule of the sodium transfer the electron again to the this radical earlier. So once this electron transfer, now it becomes a negatively charged. And once this becomes negatively charged, it abstracts the proton. Again, there is one proton from here. And now this again goes to this OH bond cleavage. It will help to eliminate the OMe group. It gives convert into the aldehyde. But the reaction doesn't stop at this position because aldehyde also electron deficient. The sodium again gives the electron to the carbon center of this aldehyde, and now it will be converted into the similar radical as like earlier seen in case of the ester. This negative charge again abstracts the proton from the ethanol. It becomes the OH. Now another electron transfer takes place. It forms a negatively charged, and once the negative charge from, it will again take the proton from the solvent, right? And it got converted to the alcohol now. Right. So this is the course of the reaction. So basically, you need to understand. So it will give the total cleavage. So whenever you have such group, so in this case, you can see. So you can directly first thing in your mind is, so first step, this will be eliminated. It get converted into the pH CH2 double bond O, and this is now converted to aldehyde. Now again, after second step, this will again convert into pH. This will be the OH, and this will be the proton and the proton. So this is how it will be give the reduction of the ester to alcohol. So the product is the B. The option B is the correct answer here. So even here, if you in case instead of the aldehyde, if you have the instead of sorry the ester, if you have the aldehyde, then also the product will be the alcohol, because aldehyde can and also convert into the alcohol with the sodium and with the sodium metal. All right, the next step is, if you remember this reaction, so this is the Sandmeyer reaction. And if you just look at the reagent combination, so we have the HBr, then the NO2, right? So what happens this HBr NaNO2? What does it give? So the HBr, that is the acid, and NaNO2, HBr, or yeah, this acid helps to form. If you have the uh, NH2, it helps to convert this NH2 into N2, N triple bond N. So that's the first step reaction. And then we have, let's say, the copper bromide, CuBr. So what happens with the CuBr? So in the same case, I will just take the same example. This CuBr helps to eliminate this N2, right? So in this case, what happens? We have the starting. So this is the pyridine, and here is the chloride. As I have mentioned earlier, this NH2 group convert into the uh, N triple bond N2 group. This is N2 positive. And now we have the CuCl, sorry, CuBr. So what happens with this CuBr? So this CuBr helps to form, eliminate this one, and the, I'll just check one more time. So this Br, here in this case, the Br will be the minus negative charge, and the Cu is the positive charge. So this bond pair of electron associated with the carbon nitrogen bond. So they are, it takes that one. So the minus N2, right? Which is get eliminated from the reaction. And now the CuBr, there's a Br negative, which attacks on that position, ipso position. So there will be a the Br, and the chloride will be the remain same, that will, which is, I'll just write the same color code. So it will help to understand. So this is how the reaction works. So whenever you see the reagent, you should be able to understand what will be the reaction in this reagent. So in this case, we have seen uh, basically two different reactions. The first one is the formation of the N2 from the NH2. This the reagent used for this conversion is the HBr plus NaNO2. So, and the next step is the CuBr. That's the Sandmeyer reaction. Sandmeyer reaction, right? The conversion of the uh, azobenzene to the any kind of nucleophile. Sorry, this copper, in place of this copper bromide. So it will be a bromination. Sorry, the bromide addition across the at the ipso position to the E triple bond N group. Any doubt in this step? All right, if you don't have any doubt, I will move to the next question, and which is again on the similar sort of the Birch reduction reaction. And in this case, uh, there are some, what we can say, selectivity kind of reaction. So let's say if you add the, so in this case also, in this case you can clearly see. So what we have, so we have aromatic system. So this is the aromatic system. The Birch reduction can goes to there also. Again, if you look at the sodium, this sodium can also transfer it on to the uh, these are the ester groups, right? So here comes the question of the selectivity. Now, the which part of this molecule has more affinity toward the electron comes from the sodium. So that's you need to understand. So anyone have any cue here? I mean, any clue that where this electron transfer? So in this case, so I will directly show the mechanism because it's kind of slightly complicated. We'll just show this one. So we have the part of center, but if you look at the electron deficiency, so this aromatic ring is not that electron deficient because of this OMe group again. And also, if you look at these ester groups, so they are more electron deficient. So the esters are more electron deficient than these aromatic systems. So that's why this whenever the electron comes from the sodium, it goes to the this ester. So here this esters, what does it do? It takes the electron from the sodium, and now so this is the electron that have taken this double bond O of this ester group. So I'll just draw this again. O Me, and so this is the double bond O. So Me. And now what happens? So when this bond goes here, this again, this also goes here. So basically, to add the position, I will draw that simultaneously. Sorry, the so this electron, one from the one sodium here goes here, from the another sodium uh, goes here, right? So this is again, this is the one, right? And now, obviously, once these two electrons on this both get uh, both position gets the two electrons, it forms the intermediate by bond by it forms a bond. So this is the newly formed bond. So this bond is getting formed. And now what happens? This O negative gives the electron. This OMe is a good leaving group. So this leaving groups get removed from this molecule and get eliminated from this molecule. Now it forms a ketone. And once this ketone is formed, again we know again there are again two electrophilic positions. The two equivalent of the sodium provide the electrons, right? So one electron goes here and another electron goes here. So again, it will forms a similar sort of a radical. And once this radical form, uh, it forms a double bond here between, right? And this double bond is now then is talk and tautomerize. So it just by tautomerization, it got converted to one is the keto and one is the alpha keto alcohol. So that's the uh, this is how it get converted into the alpha hydroxy keto group, and also the cyclation takes place in this throughout the course. So this is the some of the complicated reaction mechanism. But if you just seen this one, so what happened initially there was a two electron transfer to the carbonyl center of the ester group, then followed by the bond formation between the two ester groups, and then elimination of this methoxy group from this centers. Both the two methoxy group get eliminated. Now it leaves the two keto groups. And once these two keto groups are there, again the two equivalent of the sodium gives the electron, and it then forms a radical at these carbonyl centers. Now this radical forms a bond between them, and once this bond is formed, it get converted into the alcohol. So this alcohol it has the you can see the double bond in conjugation, so that can convert into the keto. One is the keto and one is the alcohol. So the product in the throughout this course is this one. The B option B is the correct answer here. So have you understand this how the product got in this reaction? I will wait for you to note down this mechanism. If you have any doubt, please let me know. We will discuss this again. Question. Right. So I will next move to the next question. So the next question is again. So where is the next question? Yeah. So this is the next question. So in this question, you have given a ketone group, the ketone compound, right? And one is the double bond. And also in the reaction condition, as you can see, there is a light involved. So uh, light source is the 350 nanometer. So that's obviously UV light in place of the aspirator. So if you look at this reaction, so in this case, what happens? If you directly look at this starting, so you will understand. So this is how the influence of light, the radical, it forms a radical. This double bond dead compound also forms a radical in the same manner, COOMe, and that's the C9H9. So the same here, this also forms a radical in the same manner, right? And now there will be a formation of the bond between two. So this will be the O, this is the Me, right? And here there is a new bond. This is the nitrogen, and this is the R group that was earlier. So this COO Me. So this is how the reaction. This is how this reaction works, right? So the correct option for this one is the which is the correct option. Yeah. So the correct option is this one. Next was the nourish type 1 reaction. So this nourish type 1 reaction involve, so whether alpha section of carbonyl compound, beta or gamma or none of the above. So obviously this is the alpha section is involved. So the nourish type 1 reaction involves this type of reaction. So this R1 and influence of the H nu and this nourish NT1 reaction, nourish type 1. This is just short form that I have written. So there will be a cleavage of this bond and this bond. So there will be a alpha cleavage, right? So this alpha cleavage of this bond takes place in the NT1 type of reaction. So sometime it may also represent in this manner NT1 or NT2, nourish type 1 or nourish type 2 reaction. The next question is here. So among the following, which is the correct option for the benzyme? So if you just look at the structure of the benzyme intermediate, so basically the benzyme intermediate is the one which has the 2 electron extra, right? So this is the benzyme intermediate. And if you look at the pi electron, so this pi electron is the, so how this pi electron in this case, so these are the, so there will be one electron, there will be another electron. So this is the, again, the same manner of the enzyme. And again, so the triple bond does not participate in the aromaticity in this benzyme intermediate. So that's why it obeys Huckel's rule. Huckel's rule is like those have the 4n plus 2 pi electron, they are aromatic, right? And those who don't have the, like those have the 4n pi electron, they are anti-aromatic. So, and it is n is equal to 0, 1, 2, 3, 2n. So in this manner. And in this case, so the benzyme intermediate that we have shown earlier. So this is the benzyme intermediate which I have shown also earlier. So yeah, so these are the two electrons, right? And which are not part of the system. They are not involved in the participate in the aromaticity. So that's why this benzyme electron always cancel. They have the 4 multiplied by 1 multiplied by plus 2, 4n plus 2, let's say 4 plus 2, 6 pi electron. So that's okay. 1, 2, 3. 3 pi bond means 6 pi electron, right? So that's why 6 pi electron. and therefore aromatic. So this electron actually doesn't involve. The next question about the benzyme intermediate. So the vibrational frequency for this triple bond of the benzyme intermediate. So what will be the one vibrational frequency? So this is the benzyme intermediate, and what will be the vibrational frequency for this one? So the answer for this one is the vibration frequency of the triple bond in the benzyme intermediate was assigned by Radorsky to be 1846 centimeter inverse. So this is not for the triple bond there will be 150, and for double bond if you remember 650. I just this is for triple bond. This is represent triple bond. This is the double bond. This is just approx that I have written, not exact, right? But if you if you see for this benzyme intermediate, so this benzyme intermediate is has in between, so 8646 centimeter inverse. So that's indicate the weaker triple bond than the unstrained alkyne, and vibration frequency of so yeah, strained alkyne has the vibrational frequency this one 2150 centimeter inverse, but for the benzyme which is slightly lower. Next question again on the same benzyme intermediate mechanism. So in this case, what happens? You have given a strong base with the proton, and you can see this potassium telluride can abstract the proton from here, and this proton abstraction. So once the abstract proton it forms a negatively charged, and there was a bromide. So this bromide then further get eliminated. So there will be a benzyme formation intermediate, and then this again we have obviously O T Bu negative. So because of this this is yet gonna form, right? Obviously the further step is the abstraction of proton. So better I will draw the stepwise, otherwise you may get confused. Now this is what, and there was a negative charge. Now the proton. Right, so this is a product. So via benzyme intermediate, right? So via elimination, addition, via fragmentation, obviously not fragment, via aryl cation formation, no, via aryl radical formation. So this also no. So via addition, elimination, addition reaction type of mechanism. So the earlier case, as I have shown the mechanism also in this previous slide. So once this TBU abstract the proton, there will be elimination, and then again the addition of this TB oil. So that's the addition reaction. So this addition, so elimination addition type of reaction takes place for this for the formation of this product. And if someone may ask the question, which type of intermediate involved in this one? So the benzyme intermediate is involved. So these are the some questions that I have taken for today's lecture. So does anyone have any doubts in this question? All right, we'll move to the next question. The last question of this today's section. So, if you have any doubt, please let me know regarding the question that we have solved today. So, here is the next question. So, which is based on the we have given one structure. So, you can see the structure which is in the salt form, and we have added the strong base. That's the potassium third butoxide, and then there is a furan, addition of the furan. And what will be the product in this reaction? That's you need to show. So basically, just if you look at the topic which we are learning today, which is the benzene and the structures which involved such groups. So basically, the strong base, what does it do? It will there will be a formation of such groups. This S is the positively charged. Either this proton or this proton might be abstracted. So they once abstract the proton, this goes here, and this entire group will be eliminated. So that's how the reaction might be. And I will go step by step. What was my approach to solve it? What will be my approach to to solve this question? So when I just look at this structure, entire structure, what I have observed. So this entire group was kind of living group, as you can see. So basically, I will draw the structure with this group labeled as a good living group. And so this will be the structure and the CL. And what I will draw? I will draw the good living group or also the living group I will just draw, right? So this living group will be the So this will be the living group. And now, if I just I told you to observe the structure, what it has the two protons. So these are the two protons which can be abstracted by this potassium tetrodotoxide. So now I will draw both mechanisms. So the whether it is A or the B, and I will show you which will be the correct option in this case, right? So once it just abstract, I will just draw with the some color coding. Better I will draw with this blue one. This is the, let's say, the blue proton, right? And I will draw the mechanism corresponding to that one, right? So this is the blue proton and the green proton. There are two protons here. So if this third butoxide O P B U negatively charged, I abstract this proton, what happens? And this negative goes here, and this link group get eliminated. So I will draw the structure. Here there is a chloro, here there is the OMe, and this the so this leaving group is now eliminated. And what happens? Earlier there was one bond. Now because of this, there is a benzyme formation at this position. And once this benzyme intermediate is formed, there will be a reaction of the furan. Furan, the structure of the furan. If you just look at the furan structure, so this is the furan, right? So this is the structure of the furan. Obviously, if you just remember, this is 4 plus 2 pi electron, 4 plus 2 pi electron pi addition, 4 plus 2 addition reaction. That's the seen the in pericyclic reaction is the similar manner. So what happens? So once this goes, so this goes here, this bond. I'll just draw with the some different color. So it will be easy for you to understand. So this goes here, this bond. Sorry, not like that. I'll just rotate the structure of this furan. So the furan will be like this. And I'll just draw here. See the furan, right? I just draw this if you just for simple understanding, easy for you to understand. So this is the oxygen group. Ignore the symmetry for this for now. Now what happens? This is the this goes here, this bond goes here, this electron goes there at this position and then attack here. So basically, the product form in this with this one will be looks like this. Here there is oxygen, so which is directing upward. I will just draw this with this bold arrow, right? And here there is double bond. Here there is a chloro. This is the methoxy, and the other bond will be the resonance. Basically, these are the structures which are getting formed, and this is the benzyme intermediate at this position, right? So once this benzyme intermediate here, so if you just look at the another possibility, so the another possibility is the abstraction of this green proton. So once this green proton is abstracted, so the benzyme will be like this, and here there is a chloro, and here there is OMe. This OMe basically is the electron donating group, right? And the chloro is electron again electron withdrawing group by inductive effect, but the donating by resonance effect. So in this case, which one is the stable among these two benzymes? So that's what the question there was. That's the point where the answers you get the two different answers. So this benzyme intermediate stable or this one. So this is the A and this is the B benzyme intermediate, and the intermediate which is more stable. So that's the product will be that one. So I'll just draw the product associated with the second option also, so which is then again converted into the right. So this is the product A formed from the intermediate A, and the product B. The product B will be logo. This all things will be remain same, and this is the O, right? So this is the product. So double bond here. So these are the two options. So if you look at the options that we have given, so obviously these options are incorrect. Anyway, we have already in this question, we have only one options given, which is more relevant. But if you don't have such options given, then that time the real question is which is the product going to form. So for that one, you need to understand which intermediate is stable intermediate, which benzyme intermediate is stable among these two. So the product associated with that intermediate will be the major product. So in this case, if you look at the this benzyme intermediate, so this negatively charged on this group will do localize at this position in this manner. So in this manner, and it goes to here, this position. So which is obviously symmetric with this in with these both double bond groups, right? So at this position, this is the benzyme group, and here this is the one. So which is symmetrical. But if you look at the effect of this chloro, because of this chloro, the intermediate A is the more stable because chloro also have the electron withdrawing inductive effect, and that helps to form the A benzyme as a major product. And that's why this is the major, and therefore option A is the correct option, not the one uh, which is this one, right? So got the answer for this one. So basically, the question about the stability of benzyme. So the in this reaction, as we have seen earlier, seen. So OMe, this is the chloro, This is the one benzene which is intermediate going to form, and this was the another one. So another one was like this, and Cl. So among these two, which is the A, and B, which is more stable? So there is the answer for your question. So you understand, this is the one which is more stable, and that's why the product corresponding to this benzene is the major product. Any doubt up to here? If you don't have any doubt, I will stop here for today. I will wait for you for some time. If you have any doubt, please let me know. All right, I will stop here. And if you have any doubt, so please let me know. We'll discuss that one. I will add the PPT in the same drive that I have shared with you once. So that is the one. And if you don't have any, I will just share the link for this one. Okay, link.